We're in section 4.3. We're almost finished. We have already talked about the definition of a logarithm. That was the first goal, so we can check that one off. We've already solved logarithmic equations. That was the second goal. We've already graphed the basic log function and transformation. And so now we're here at the last goal, which is to apply properties of logs. There are 5 properties. 2 of them you already know, and then 3 of them are new. So I wanted to separate them out. What you already know is, for example, that the log, well, you already know the log base 5 of 1. What is it? Remember, this means 5 to what power makes 1? And so the answer is 0. 5 to the 0 makes 1. And so in general, what we can say is that for any base a, where a is positive and a is not equal to 1, log base a of 1 is equal to 0. And so this property has a name. It's called the logarithm of 1, or I'll just shorten that up and just call it the log of 1. And then the other property that you already know is something like log base 5 of 5. 5 to what power makes 5? That's the first power. And so we can generalize that a little bit. If we have base a, we would write log base a of a is equal to 1. And we can call that property the base a log of a. Okay, so those are good to remember. And then here are 3 more properties of logs that are not so obvious. There's a product property, a quotient property, and a power property. And actually you can see all 5 properties on page 441 in the textbook. What does the product property say? It says if you have the log of the product of x times y, here it might be helpful to put parentheses around the x times y to show that we're taking the logarithm of the product there on the left side of the equal sign, and on the right side we've split it apart so that we have just the log of x and just the log of y with a plus sign in between. The multiplication becomes addition. The log of the product is equal to the sum of the logs of the 2 numbers. And similarly for the quotient, the log of a quotient is equal to the difference of the logs of the 2 numbers. And then the last one is the power property, and it just says that if you have the log of x to the r, then that r can come down in front as a coefficient. Okay, I'll actually prove the product property at the end of this video, but for now let's just take it at face value. Actually, let me give you a concrete example that might help you to understand this better. So what we're saying here in this first property, the product property, what we're saying is suppose that a is 2 and x is 4 and y is 8. Suppose x equals 2. I'm sorry, that's not x. That's a. Suppose a is 2, x is 4, and y is 8. I've chosen these numbers carefully so that the calculation will be straightforward and we can see that we get a true statement. So specifically, what we would get if we plug that in is we would get log base 2 of 4 times 8 is equal to log base 2 of 4 plus log base 2 of 8. And I just want to verify that that really is true, at least for these numbers. So let's just simplify the left side and simplify the right and see that it works. So on the left side, order of operations says multiply first and get 32. You'd have the log base 2 of 32. And then what is the log base 2 of 32? It's 2 to what power makes 32? So you can verify that 2 to the 5th is 32. 2 to the 5th power is 32. So the left side simplifies to 5. And then on the right side, log base 2 of 4, 2 to what power makes 4? Well, that's 2. And 2 to what power makes 8? That's 3. So log base 2 of 8 is 3. And 2 plus 3 is 5. So in fact, the property works. So that looks good. That makes us feel a little more comfortable maybe with using the property. And then the other thing that you might ask is, what is this property good for? And so let's write that the property is good for solving an equation like the log base 2 of x plus the log base 2 of, say, x plus 3 is equal to, I don't know, we could just write 4 over here. I just made these numbers up, so we could definitely go through and solve it. We're not going to do that right now. If we did solve this particular equation, the answer might not be a nice integer value. We might get some decimals or some radicals. But regardless, this is the type of equation that we need to be able to solve in section 4.5. And so we're going to learn the property now, and then we're going to use it later on. The first step in solving this equation would be to apply the product property so that we write the left side as a single log instead of 2 separate logs. Okay, one more thing. There's no property for the log of a sum or the log of a difference. So don't get those mixed up. The property is when you have the difference of 2 logs or the sum of 2 logs, but that's very different from this right here. So be careful. Don't make the common mistake and try to apply and try to make up a property or apply some property that doesn't exist to an expression like this. Okay, so in example 6, we're going to use properties of logs to rewrite the expressions. And so here in part A, we have the log of a quotient, 12 over 5. And so we can just write it as a subtraction problem. We can just write that as the log base 6 of 12 minus the log base 6 of 5. And really, that's all we need to do. Okay, and in the next one, the next one says the log of the square root of 3xy. What's the base this time? There's no base written. I don't think we've talked about it in this class. Maybe you heard somewhere else that if you just have log and no base, then that implies that the base is 10 and it's called a common log. So I'll say that again in the next section. But for now, we are not too surprised to see log without a base written. So at any rate, this one is just a little bit tricky. That square root needs to be rewritten as a power so that we can apply the power property. And so what we're going to do is we're going to remember that the square root is the same as the 1/2 power. And then maybe you can see 2 more steps. So now you can see the power property says we can bring that 1/2 down in front. And then the product property says each of these 3 factors, 3, x, and y, can get their own log with an addition in between. So 1/2, and then we're going to multiply that by the log of 3 plus the log of x plus the log of y. And that's our answer. Does that look okay? You could go ahead and distribute the 1/2 to each term inside the parentheses, but that's not necessary. It's okay, but not necessary. Okay, and then in the next example, we're going to do something similar, but a reverse process. We're going to take several logs and put it together as a single log, right? And in example 6, we took a single log and wrote it out as more than one log. Now take 3 logs here in example 7, rewrite it as a single logarithm. And so we can take the first 2, that's 2 logs being added together, and we can write that as the log of a product. So that would be x plus 2 times x. And of course the base is a. And if you wanted to, you could put some emphasis on the order of operations by putting brackets around x plus 2 times x. Okay. And then there's still a minus log of 2 at the end. And so now, what do you have? So now you have the difference of 2 logs. So 1 log minus another log, and so we know that we can rewrite that as the log of a quotient. So x plus 2 times x stays in the numerator, and 2 goes down to the denominator. Don't forget the base a. And again, if you want, you could put brackets around it, although that's not really necessary. Okay, and we're already done. And again, we'll practice this more in section 4.5 when we're solving equations. Okay, so that takes care of the property of logs. Now I just wanted to do one more thing. I wanted to offer a proof for at least one of those properties. We don't have to prove all of them here, but we could call it an aside or a footnote. Let's prove that the log base a of x times y really is equal to the log base a of x plus the log base a of y. And so let's just get right into it. There's a clever step. So mostly the proof relies on properties of exponents, and you might be able to guess that because the log is just the inverse of an exponential. So if we know properties of exponents, then there has to be some correlation to some similar property of logarithms. Property of exponents is at the heart of the proof, and then there's just a little clever naming convention to get us through. So the clever thing is to say, let's let m equal the log base a of x, and let's let n equal the log base a of y. And then that's going to allow us to work with those two logs the way we want to. And in particular, you know, if log base a of x is equal to m, then there's a corresponding exponential, a to the m is equal to x, and over here a to the n is equal to y. And so then what we can do, then we can say that the log base a of x times y is equal to, and we'll just rewrite it, right? So we're starting now with the left side of our rule, and we're going to manipulate it. We're going to go through a series of steps to get to the right side, to get to this over here, and then we'll know we're finished. Okay, so what is x? Well, the way I have defined m means that x is a to the m. And so I can rewrite x as a to the m. And I can rewrite y as a to the n. And then I can apply the property of exponents inside the parentheses. Property of exponents says that I have to add m and n together. Okay, very good. And then can you see what's next? The theorem on inverses says that the log base a of a base a exponential will cancel each other out, and we'll just be left with m plus n. M plus n. So we talked about this a little bit in a previous video, that the base a exponential and the log base a cancel each other because that's what opposites do, or that's what inverses do. And so we're just left with m plus n, and then we can substitute. Well, m is the log base a of x, and n is the log base a of y. And sure enough, that's exactly what we were trying to show. So the little shaded box just means that my proof is done. Look, I've started here with what's on the left side of the equal sign, and through a series of steps I wound up with what's over here on the right side. So I've demonstrated that the two are equal.